Today we're going to take a look at section 10.3, and we're going to take a look at parametric equations and calculus. So as a general sort of what are we doing? In Calc 1 we learned how to calculate slopes of y equal f of x, and we'd like to do the same for plane curves. That's where we're going to start. We're going to move into a little bit of antiderivative stuff toward the end, but we're going to start with slopes. So this is the parametric form of the derivative. And the first one is just as you would expect it. So if you have a smooth curve C, and it's given by the equations x is f of t and y is g of t, excuse me, then the slope of C at xy is dy dx. dy dx is the derivative of y prime of t, over the derivative of x prime of t. And that's fabulous, just like we would expect. Second derivatives are a little bit messier. So we've talked about this notation, but not really in this class. We talked about it because you guys were talking about some partial differential stuff in here with me one day. This is telling you that you have the derivative, the second derivative of y with respect to x twice. d2y dx2. Now, we encounter that notation in Calc 1. We just don't really spend a lot of time there. We just go back to that, f double prime of x kind of stuff. So this is the d dx of dy dx. But dy dx is dy dt over dx dt. So what you see here is you see a chain rule kind of component coming about in this. So we have to take our dy dx that we would have gotten, say, from here. Where was it? Over here, right? Like there. And then we take the derivative of that with respect to t. Okay? It usually ends up giving you a quotient rule because this is often a quotient, right? So you end up with the quotient rule a lot of the time. Sometimes some things simplify and you don't, but a lot of the time. And then you divide that by dx dt, or sometimes you'll see me write, or you'll see your book change the notation down here into just doing it x prime of t. They'll say x prime of t there instead of that. That's another notation you can see in the denominator. Okay? Ready to give it a try? The first one's real straightforward. It's just a dy dx problem. So we're given on all of these a set of parametric equations, right? So x is t squared, y is 7 minus 6t, and we're asked to find dy dt, dy dx. And so the first thing we do is we find the derivative of each of these respectively. So what is that yellow okay for you guys to read? It's good? It's not like harsh to read? Okay, then I'll use yellow on this. Okay, so what is the derivative of x with respect to t? 2t. And how about y? Negative 6. And then to do dy dx, we actually divide y prime. I'll write this down this time. Divided by x prime. That's what we're doing. So the y prime, we just said, was negative 6. The x prime was 2t. And this becomes what? Negative 3 over t. Yep. Okay. So we took two derivatives and we divided them. That's all we do for finding dy dx.
Sorry.
It's okay. Okay, things get hairier on the next problem because it doesn't just ask for dy dx, but it also asks for the second derivative, right? So in order to find the second derivative, if you'll take a look at this though, we need the first derivative because it shows up inside of here, right? So even if it hadn't asked us to find the derivative, we'd have to do that because it's part of the process as we continue on, just like it is when we're doing second derivatives in general. But for this one, it's actually hinged upon it in a slightly different way. So we're going to start again with finding the derivatives of each of these. So what's x prime and what's y prime? Let's start with the top one, x prime.
Negative 2 sine 2t.
Negative 2 sine 2t. And y prime?
4 cosine 4t.
4 cosine 4t. Okay, so as we work with this one, we're going to be careful about our signs because they are going to oscillate within what we're doing. And so finding dy dx would be to take the 4 cosine 4t and divide it by negative 2 sine of 2t. Is that okay? If we simplify a little bit, what are we going to get?
2 cosine 4t or sine 2t? Can you?
We'll talk about that part. You're about to ask a good question. I missed something though, or you
Oh.
missed.
2t. It's negative.
Oh yeah, let me fix that.
And it's a negative 2.
I lost this. That was the one I noticed. I wrote that down wrong. 2 and a negative here. Okay, did I get all the pieces back there now where they're supposed to be? Okay, you ready? Because the next part's the part that gets messy. Okay, so now we're doing D2. Oh, there's one thing missing on here.
Are we able to simplify that?
Okay.
T is equal to pi over 4.
Yeah, this is what's missing, and then I'll answer that question, which was about what Adeline was about to ask too, pi over 4. Okay. Are we able to simplify this? What do you guys think?
No.
No. The answer is no. The angles don't match. Now, is there a way that we could somehow get them to match? Yeah, we could use a double angle property from trig, that kind of stuff. Remember what I'm talking about? Some of you are like, yeah, I remember. Do we have to do that? The answer is no, you don't have to do this. This is perfectly okay to leave it this way for what we're doing. But can it be simplified? Yeah, it can. The one that I remember is a double angle for sine. So the sine of 2a is 2 sine a cosine a. That's one I remember. But the double angle for cosine is a little bit less clear in my mind as a remembrance, right? So, yeah, can we change it? We can. Are we going to? No, we're not. Okay. There was something that I skipped over in the directions. I noticed it in my notes. It actually says at the given parametric value, this was one of those things that got left off. So if you do not have t equal pi over 4, it means you printed your notes before 11 o'clock. That's what it means. So just write it in. It should have been there. All right. So it says at the given parametric value, what it's meaning is that it wants to actually find the dy dx in this case at the value for t equal, and they gave us pi over 4. So we're going to actually evaluate this at pi over 4. So I have negative 2 cosine of 4 times pi over 4 over, did I write that right? Yeah. Sine of 2 times pi over 4. So the top one becomes pi, so I have cosine of pi. What's cosine of pi?
1.
It's 1, and I have the negative 2 in front, so I have negative 2 times 1. How about sine of, and then pi over 4 times 2 would become pi over 2.
Isn't it negative 1? Yeah.
A second here.
Negative 1.
We have the cosine of pi. Yep. Negative 1. That good? Okay. Do you need to go get some more water?
No, it's not working. So.
Okay. All right. Okay. How about the sine of pi halves? Yeah, that one's 1. So this gives us a ending slope of 2. So the slope at pi halves, or pi fourths, excuse me, the slope at pi fourths is actually the number 2. Very good. Now we're ready to do the other one. I'll change colors so that we can distinguish it. So now we're going to do d2y dx2. And just so that we remember what we're doing, I'm going to write out what it is. This is the derivative with respect to t of dy dt. And we divide that then by the derivative of x with respect to t. So we take this piece right up here. This actually it's the one that we've squared in, or I squared in up here. And we're going to take the derivative of that with respect to t. And you see the quotient rule immediately, right? I've got a quotient, so I'm going to have a quotient rule. Great. Okay, so I need the denominator. So that's the sine of 2t times the derivative of the numerator. So what's the derivative of the numerator?
8 sine 4t.
8 sine 4t. Yep, the sign changed, right, from negative to positive because the derivative of cosine is negative sine. And we get another factor of 4 that's multiplied by that 2. Cool. And then minus, so that's low d high. So we have the denominator times the derivative of the numerator. And now we're going to do the opposite. So we need the numerator.
Minus 2 cosine
and times the derivative of the denominator.
Two cosine 2t.
Good. 2 cosine 2t. All over sine squared of 2t. Yeah? Sine 2t, sine 2t. But then all of that is over,
Oh my gosh, wait.
yeah, are you loving it? All of that is over dx dt. What was dx dt? Well, we wrote it down up here.
-2 sine 2t.
-2 sine of 2t.
Well, it's just got worse.
It just got worse, yeah. Okay. Some of this cleans up, some of it doesn't. So we're going to take a minute to try and clean up the things that do. So the first one, I can move the 8 to the front. So I have 8 sine 2t sine 4t. Again, could I combine the sine 4t and the sine 2t? Yes. There's an addition angles property, like angle addition property. Like we have that back in trig, but that's not our goal right now. So if you're looking at a back of a book or something like that, or the answers, they're probably going to do that. I'm fine with you leaving it just like that, right? If we have some things cancel out, we'll do that. But I'm not asking you to consolidate this, okay? Over here we have, it's addition now, right? And we have 2 and 2, so that's 4. And then just so that they're in the same order, I'm going to put cosine 2t, cosine 4t. Not because it really matters, but then it's in the same order as the other one. All right, so we're dividing by the sine squared of 2t and another -2 sine of 2t. Now, when we divide by a division, we'd multiply by the reciprocal. So I'll show this in here, right here. But basically what's happening here is that we're going to multiply by 1 over -2 sine 2t. And that's going to move. Sorry. These will cancel, that's the whole point, and then it moves that to the actual denominator of the top part anyway. It becomes part of the other denominator. So they end up being multiplied, and they match. They're both sine of 2t. So I had sine squared of 2t times sine of 2t. How many sines of 2t did that give me?
Sine cubed 2t.
Yeah, and I have a -2 in front of it.
I'm confused as to where the -2 sine 2t comes from.
It comes from this right here. I have to divide by dx dt.
Which we found earlier.
Yes. And the reason this is happening, I mean, you could say it's happening because there's a formula for it, but the reason that the formula is coming about is because we're taking another derivative with respect to x again, and therefore dividing by the x prime again. Yeah, Noah?
I just wanted to double check. So d dt times dy dt.
It's not times. It's the derivative of t, the derivative with respect to t of that. It's like function notation.
But that numerator is
Yes.
the same as taking the derivative of dy dt.
Yes, yes. And that's what this is saying. It's saying I'm taking, I don't have a good way to write all this, but I'm taking the derivative with respect to t of this quantity. Oops.
And
So-
dy dt is not the derivative of y.
There is a typo. That should say dy dx.
Oh, okay.
That's what's
okay,
wrong.
Okay. That's okay.
This is saying it should say dy dx.
Yeah, that is why I was
Sorry,
not understanding.
that's
how
what's
we
going
got
there. It was right over on my other screen, I believe. Yes, it's right on my other screen.
Yeah.
I just typed it when I wrote it on this
What did you
screen.
have up there?
dy over dt.
Oh.
And that's why I was like, wait,
Yeah, that would be
why are
confusing.
we? I was like, wait, why are
Yeah,
we taking
okay.
that one? But
Sorry.
No, I got you now. I got
So
you.
are we good? We got all my mistakes fixed. Thank you. Appreciate it. So we're back to having a -2 sine cubed of 2t here, right? The only other thing we could do is what? I mean, do you see something? There is one more thing we can do.
You could reduce it.
We could reduce it. There's a 2 in that denominator, and each of the coefficients in the numerator's also got a factor of 2 in them. So I could reduce them. So I have this 2, this 8, and this 4. You could even move the negative up if you so desired.
Yes.
I am rapidly losing space. Okay, I'm good with that, I think. Okay, so the last version of this then that I would really have to, or be able to do is 4 sine 4t sine, sorry, 2t, 4t, we'll keep in the same order. Sine 2t, sine 4t, and then plus, and then I'd have 2 cosine 2t, cosine 4t, and that would all be divided by negative sine of 2t. Sorry, sine cubed of 2t. Okay, but what are the directions I'm supposed to do? Find those.
Concavity.
Find those.
So concavity is what's.
Okay, the directions don't say anything about concavity on this one.
Yeah.
Given parametric value, right?
Oh, sorry. I was looking at the ending of my directions. Yes, they say it there. I'm sorry. Slope, concavity. But it says, the one part that I wanted us to highlight on is that it's at the given parametric value, right? That's the part we haven't done. Sorry, I was thinking about my next direction sets that are coming up.
Pi over 4.
Now we just plug in pi over 4, right? So now I need to do d2x y, let's do y, d2y dx2, and we're evaluating this at t equal pi over 4. Okay, so pi over 4 into all of these. So I'm going to try to do this without having to write all the pi over 4s in because my space is so limited. I got a 4 at the beginning. I'll start with that. So if I put in pi over 4 into the sine 2t, that gives me sine of pi over 2, which is, where did this one? 1 for pi over 2.
And then the next one's just 0.
Okay, and then the sine of 4 pi, or the sine of pi, 4 times this would be 0, right? And then I have plus, I have a 2. So now I have cosine of pi over 2.
That's 0.
That one's 0. Cosine of pi would actually be 1, positive 1, negative 1, negative 1, and then
0.
it's going to be 0. We do want to make sure the denominator doesn't give me 0, or I'm going to have problems, so let's finish the denominator piece out at least to identify that. So it's a negative, and then the sine value at pi over 2 is 1, so it's technically 1 cubed, but I don't get a 0 in the denominator anyway. So 0 in the numerator, 0 not in the denominator. This is giving me a 0. What does 0 mean about the concavity?
It means it's changing at that point.
Maybe.
Or it's just flat line.
Okay, so it's a possible concavity change, or it's a possible inflection if you want to say it that way. It's a possible inflection point, possible change in concavity. We don't know for sure. It could be a really flattening out curve. Like the one that you want to keep in your mind is something like y equal x to the 4th. Y equal x to the 4th looks like a parabola with a really flat, U shape on the bottom, like the bottom of the U is really flat. It has a second derivative that's 0, but its concavity does not change. Can you picture that? Yeah. So they don't always change in those places, but those are the places where they do change or could change. Okay. Let's take a look at the next one. Along the lines of finding slopes, we find tangent lines, right? Think back to Calc 1. That's something we did when we found slopes. So we're going to find an equation of a tangent line at the given point on the curve. Now, this is not written into my notes here, but I wrote them in again before 11 o'clock, so they're not on my slide. The first one's given point is at the point 2, 0, and the second one over here was at the point 3, negative 2. Now, the first problem that we did told us a t value. This problem doesn't give us a t value. What's it giving us?
X and Y value.
It's giving us the x and the y values. So we actually need to figure out what the t value is to make this work. So before we get there, this is all about slope. We find slope by taking derivatives, so let's do that. So what's the derivative of x? So what is x prime?
4t cubed.
4t cubed. And y prime?
3t squared plus 1.
3t squared plus 1. And then dy dx?
3t squared plus 1 over 4t.
Okay, everybody good so far? So I want to find a slope. Well, actually, I want to find a tangent line. I want to find a tangent line to my curve at this particular point, but I only have the slope in terms of t. Are you with me? The slope that we just wrote down is in terms of t, but the point is an ordered pair with x and y. So what do?
Can you solve for t?
We've got to solve for t. Yeah, and we talked about that in the last section, but we didn't do a lot of it, at least not in class, about how we do that. So we need to have our x value, which is 2, equal the t to the fourth plus 2, and our y value, which is 0, to equal t cubed plus t. Now, it's a system of equations, right? In theory, we might be able to just solve one of these equations and find t. But sometimes when we do this, we'll have multiple options for what t can be from one equation, especially when we have squareds and powers of 4s and things like that. And we need the other equation to determine which one we're using. So on this one, just look at the first equation. If 2 is equal to t to the fourth plus 2, what's t have to be?
0.
Has to be 0. Does that work in the second equation?
Yes.
Yes, it does. So these two things tell me that t is equal to 0. Now that doesn't answer my question, but at least tells me the value for t I need to put in order to make this work. So I need to do dy dx at t equal to 0. So I have 3 times 0 squared plus 1 over 4 times 0 cubed. And what happens?
Effect 0.
We get a 0 in the denominator. And you're right, this is undefined. What kind of lines are undefined? Vertical ones. So this tells me I have a vertical line. So what vertical line goes through the point to 0?
X is equal to 2.
Yeah.
That's our answer for part A.
That's our answer for part A. We're looking for a line that goes through the point and has the desired slope.
Satisfy the conditions.
Yep, satisfy the conditions, you bet. All right, the next one's a little bit more typical, right? Undefined slopes are very rare, maybe in terms of like actual examples that show up with them, but they could. So on this one, I have an x value that's 3, so 3 is equal to t squared plus 2. And on the other one, the y value is that negative 2 is equal to t cubed
Wait.
plus t. Is that right? Yeah.
4t. I mean t to the fourth plus 2.
No. Oh, yes, t to the fourth. That's the part I missed. You're right. Okay, so take a look at just that first equation. Do a little bit of algebra. I'm going to shift mine down so I can show it as well after you've thought through it. What's t?
1.
Negative.
Okay, negative 1 or 1 from the first equation, right? From the first equation, we have two options. T could be positive or negative 1. Maybe you're looking at that and you're just sort of process by elimination, or maybe you're actually doing algebraic steps where you're saying, oh, I need to subtract the 2, and then I need to do the... That's fine. Whatever it is, there's two options. But now I have to figure out using the other equation which one works. In theory, it could be both, perhaps, but this one's not. Which one is it?
Negative.
It's negative. The t equal negative 1 is the only one that will satisfy the second equation. So here, t will have to equal negative 1 to make it actually work. Okay, is that all right? So now we're going to take that same dy dx and we're going to evaluate it at t equal negative 1. So dy dx at t equal negative 1. So I have 3 times negative 1 squared plus 1 over 4 times negative 1 cubed. What does that give us?
-1.
Yep, I get negative 1 from that. What did I just find?
The slope.
Found the slope. How do I find an equation of a tangent line then?
Point slope.
Yeah, point slope formula. So, or you could do slope intercept if you wanted, and to do it from that perspective would work too. But point slope is the way that I will do it. So I have y minus the y value, so it would be y minus negative 2, so y plus 2, equals my slope, which is negative 1, and then x minus the x value is x minus 3. So Do some quick simplification, showing whatever steps you need to get there. That's definitely part of it. What's my y-intercept?
That's one.
Wait, no, negative
Try again on your sign.
4.
It's 1. Look again, Maggie. You're okay.
So you can't leave it in point slope form?
We'll solve it for y equals.
Okay.
Yeah, we'll put it in the slope-intercept one. Did you find it, Maggie?
Yes.
Okay.
I just
That's okay.
How to add
Sorry.
numbers.
Okay, next one. Number 4. And you knew exactly what I meant, didn't you? Number 4. So we're going to find all points, if any, of horizontal and vertical tangency. Okay? So all the problems that are talking about tangency, we're doing derivatives. So we're going to start by doing derivative here. So what is the derivative of x?
2t.
2t. And the derivative of y?
4t cubed minus 4.
Excellent. Everybody good? Okay, they put them in order of horizontal and vertical, so that's how we will do this as well. Our horizontal tangency. What does it mean to have a horizontal tangent line?
It's equal to 0.
What's equal to 0?
The slope.
So this means the slope is 0. Okay? So let's think about, I'll write it up here at the top, dy dx. dy dx is what in terms of what we're working on? What's on top, what's on bottom?
Rise over run.
Rise over run, but in terms of the derivatives with our parametric equations.
Y over
Yeah, y prime over x prime, right? This is what we're doing. We're doing derivative of y on the top of derivative of x. So if we want a slope that's 0, what would have to happen in that equation to get a slope of 0?
Y prime equals 0.
Yes, so this would mean that my y prime would have to equal 0. Well, we know y prime. We just found it, right? My y prime is the 4t cubed minus 4 would have to equal 0. So we're going to solve that. So if you simplify and so forth, what is t going to be?
1.
T is 1. Okay, that is not the answer to the question. What's the question specifically asking us to find? A point. I found a t value. So what do we do to find the point?
Plug in 1 to the
Right. We use the parametric equations and figure out what's that corresponding point. So I have 1 squared minus 1, and for y, I have 1 to the 4th minus 4 times 1. So what are my x and my y coordinates for this?
0.
Mm-hmm.
And 3.
Yes. So the point of horizontal tangency, right? In Calc 1, we often talk about it being a max or a min often. Doesn't have to be, but it's often a max or a min. Would be the point 0, negative 3.
So how would it be more? This is final points.
If we had solved something where we had a plus or a minus.
Oh, okay.
Yeah, like imagine if you had a curve, like the circles or ellipses that we've been working on, you'd have a horizontal tangency on the top and on the bottom, but their x coordinates would match.
Okay.
You could have that happen. Yeah. All right, so that's horizontal. Now we're going to do vertical. So vertical tangency. Well, how do I get, taking a look at that equation for slope, a vertical line?
Not at 0.
Yes, so this would mean that I need the denominator to equal 0, and my denominator is,
2t.
in general, it's x prime, right? But yeah, it's 2t, just 2t. So 2t has to equal 0, and so that would happen at t equal what?
0.
0. And again, that's not the final answer. I need my x coordinate, and I need my y coordinate. So x is 0 squared minus 1. Y is 0 to the 4th minus 4 times 0.
Negative 1, 0.
And that point would be negative 1, 0.
Was there a reason you wrote A at the top in front of both, or was that like an A and B?
I was writing it as A and B as they were to my two different parts of my problem.
Okay.
Thank you.
It's A and A now.
It's A and A. I mean, They didn't give me any letters, so I made them up, right? Yeah. Okay, are you ready? This one's messier. How come? It's actually not because of the natural log, although there is a natural log in it. Why is this one going to be
We have
messier?
to determine the range between the two values.
That's not why.
I don't like this.
Okay, what a T interval is.
yourself.
You know,
T interval just means what are the T values for which this is going to happen.
Is it because this is concave up and concave down?
Why would that make things harder?
Because I don't
Second
remember how to do
derivative.
that.
Because
It's the second derivative.
second derivative. What did we learn about the second derivative like 3 problems ago?
It's so if it's positive, it's concave up.
Okay, well that's what it is.
Quotient.
It's a lot of work because there's a quotient involved.
Yep.
Okay, so it was over here, the second half of that slide. That was the second derivative.
We have to
I'm
take
not
one
sure.
out.
Are you with
I'm
me?
not sure what
Okay,
we do.
so I think we have time to do this one at least. Let's give it a go. We do need to know the actual derivative first. So we need x prime, and we'll need y prime. So what is x prime?
2 minus 1 over t, or plus.
2 plus 1 over t, right?
The other one's 2 minus 1.
It is. And what is dy dx?
2 minus 1 over t over plus 1 over t. Did you simplify that and multiply it by t?
Absolutely. You bet. That's exactly what we're going to do. So yeah, fractions within fractions, those are called complex fractions, and we will simplify that by multiplying numerator and denominator by t. What will that end up giving us?
2t minus 1 over 2t plus 1.
Perfect. Okay, that's the derivative. Again, didn't actually say find the derivative, but we have to, right? So we're going to do the second derivative now. So d2y dx2. So this is d dt. I'm reminding you what it is, of dy dx over dx dt. Yeah. So the first one, the numerator means the derivative of the first derivative. Okay, my first derivative is over here, the 2t plus 1 over 2t minus 1. So I need the derivative of that. Somebody walk me through what you would have.
You get 2t plus 1.
Mm-hmm.
That's the denominator.
Yep.
Multiply that by 2.
Good.
Derivative of the numerator. Minus 2t minus 1. It's the numerator. And multiply by 2 because that is the derivative of the denominator.
Fantastic.
And then you're going to have 2t plus 1 squared. So that is your denominator squared.
Yes, sir. Good job. Okay. And then, sorry, go ahead, Adeline.
I was trying to ask for the dx dt. Could we multiply that by t so we don't have
We can't right now. The only reason we can do that over here was because we had a numerator and denominator, which meant we multiplied the fraction by 1.
So it has, you have to write it as 2 plus 3.
For now. We'll fix it in a minute.
That's
Yeah, we will fix it. All right.
No.
Okay, as Alex pointed out, we're running out of time, so let's focus. Okay, 2 plus 1 over t is my denominator because it's x prime. Okay, but just like Adeline said, that's not real pretty. We can make an adjustment right here, though, if we would like, and I think I will for the sake of space. I can actually move this into the denominator of the original fraction just fine. We saw that happen on the previous problem, right? So we could do that. But like she mentioned, what can we do about that t on bottom? Well, we can multiply by t now. We'll do it on the top and the bottom of our fraction. But before we do that, can we clean up the top? Because it will clean up a lot.
Yeah.
So do a little bit of simplification on that top and tell me what you end up with. Did you get 4? That top is just 4.
Nice.
So that's a very nice simplification for our top.
And couldn't you just, for that bottom right piece, go and make that 2t plus 1 over t, and you can combine all those, and it's 2t plus 1 cubed? And
Yes, that's exactly what we're going to do. You're reading my mind. I'm going to do it in a little bit different visual way. We're just going to multiply t like that. So if you remember, right, distributive property, if I distribute it into here, because this piece is already being multiplied by the 2t plus 1 squared, I don't need to distribute it to both pieces. I'm just multiplying the back two together first. So I end up with 4t on top. And then we end up with 2t plus 1, and Caleb's exactly right, cubed on bottom.
That's much nicer.
Okay, it actually boils down to a really nice ending result, though. And in some ways, you're going to probably be like, seriously, all that work for that result? But that's okay. So concavity, we're talking about concavity. So what are we looking for next? We found the second derivative. What do we want to know?
When it's positive.
Well, we want to know when it's positive and it's negative, but we can find that by doing what?
Finding the zeros.
When there is 0. So I'm looking for when this is 0, or there's one other possibility.
Undefined.
Undefined. So this is 0 or does not exist. That's what we're looking for. Changes in concavity, if they occur when their second derivative is equal to 0 or when the second derivative doesn't exist. Think about asymptotes, right? You can have a change in concavity if you flip it over an asymptote kind of thing. When does this equal 0?
When it's at 0.
Right, when t is equal to 0. We're going to come back to that in a minute. When does this equal does not exist?
-1/2.
When t is equal to -1/2. Okay, everybody good so far? Look back at the original x and y. What can you tell me about t equal to 0 and, in this case, t equal to -1/2?
Oh, it makes
Why, Robert?
Because t is bounded by, like, it can't go past 0. That's
Right. It's a natural log function, right? Natural log's domain is 0 and up, and not including 0, right? The domain over here I'll actually write it this way, is t is greater than 0. So the two values for t that I got, which are the possible changes in concavity, are not in the domain. What does that tell you? Not that there is no concavity, but there's no change in concavity, okay? So this tells us there's no, so this is that therefore marker. No, therefore there's no change in concavity. So that means whatever the concavity is, it's the same everywhere. So how can I figure out what it is?
Set it equal to 1.
Set what equal to 1?
T.
T. Okay, you can let t be anything you want to do this process, right? So we might as well let t be something friendly, and 0 is not an option because, it's not in the domain. So t equal to 1 is a good place to go. So we can choose a t value. So we're going to let t equal to 1, and we're going to figure out, well, t equal to 1 in what? Where am I putting t equal to 1 in?
The second derivative.
In the second derivative. So I'm taking d2y dx2, and I'm evaluating it at t equal to 1. And what do you get?
A positive value.
You get a positive value. You get something bigger than 1. I'm sorry, bigger than 0. So what does that tell you?
It's concave out from negative infinity to infinity.
Is it?
Or from 0.
Anything above 0.
So concave up from 0 to infinity. And that's the t interval that it was talking about, right? An interval for t. I know what's coming next.
Isn't that just for the natural log?
Huh?
Isn't that just for the natural log?
Yes. Yeah. Okay. So we will write down the definition next, and then we'll pause. Okay, and we'll pick up next time. We'll talk about homework in just a sec. This is actually a pretty nice place for us to start and stop, is because we're going to switch gears on this next part anyway, and we're going to start looking at something that's not derivatives. Instead, it's going to be antiderivatives. So this is arc length in parametric form. You've actually seen arc length before. We do it in Calc 1 as well in Chapter 4. If a smooth curve is given by equations, x equals f of t and y equals g of t, as long as the curve does not intersect itself, then it's okay. Then the arc length of c over the interval is the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt.
dt is not under the radical, is that correct?
Correct, it is not. Okay. If you go back and you look in Chapter 4 at arc length formula, this is very similar to the one presented there. What do you see some things here that are sort of feeling like it's, I don't know, familiar to you?
Pythagorean.
Looks like Pythagorean theorem, doesn't it? And also, I had a discussion with a Calc 1 student this morning before too, right? Like you can't cancel the squares and the square roots, right? It doesn't work like that, yeah? So we wish we could, but it doesn't work like that. But you see that even in the midst of finding an antiderivative, we're going to be finding derivatives, right? Isn't that fun?
Yeah.
All right, so we'll pick back up on that next time.